I'm going to talk about how to generate fake or synthetic data. Our purpose here is to demonstrate regression in other videos within this playlist. I am, of course, not advocating that you mislead people, but it sometimes helps to generate fake data so you can test algorithms and also visualizations. So I'm going to create 3 data sets. I call them XY data. What I mean is that they're pairs of XY data points. And I'm going to create a linear data set, a quadratic related data set, and a exponential rise. Let me show you what I mean. So I'm going to define some functions. So this is a linear relationship between x and y. And then I'm going to define an exponential. In earlier videos, I pointed out that the first 2 functions can be studied using linear regression techniques. We can fit data according to those 2 functions using linear regression. And the third function is going to require nonlinear regression. So if I'm going to say just arbitrarily, my x data are going to go from 1 to 10, I'm going to say y series 1 is just going to be f1 of x series. This is not quite fake data yet. I guess it depends on your definition. But I'll just remove the semicolon so that we can take a look at what the output is. Let's run this. Looks like I typed something wrong. Oh, I haven't defined my constants. So let's just define the constants. I picked numbers earlier just so that they made the curves look like I wanted them to look. This required a little bit of fiddling, but I wanted the range of the data to be similar between the, the different data sets. Okay, maybe that will work. Okay, so what we're doing here is we defined a single set of x values in x series, which is 0, 1, 2, 3 through 10. And I'm using the functions f1, f2, and f3 to generate curves or generate data according to the functions, where y is a function of x. Now, this will have no noise, so it won't really look like a real data set, but let's just plot what we have just to see what things look like right now. I'm going to plot them on 3 different axes. Let's make sure that works. Okay, that's what I wanted to see. Why don't we label our axes as well? And so this would be quadratic, and this would be exponential. I called it a power law. Okay, and something is wrong. Oh, Y label, not X label. Okay, so I mentioned that this is not really what data look like. All it really is well-defined functions evaluated at specific points. In order to make it look like real experimental data, we'd have to introduce noise. There would be some scatter about the curves. So let's talk a little bit about how to do that. I mentioned in a previous um, video in the same series, in the same playlist, that it is important that your noise vary according to the Gaussian distribution. That's one of the assumptions behind least squares fitting. So I'm going to show you how to generate Gaussian distributed noise in Matlab. So I'm going to ask for 10,000 data points. And in fact, let's plot that. I'll show you what you get. Oops, rand n is the name of the function. So this is normal distributed. By default, your mean is 0 and your standard deviation is 1, which is why after about 3 standard deviations, your intensity is 0. So this is just a histogram of the numbers output by rand n. If we want to expand the standard deviation, we just need to scale. So for example, if I multiply by 5, then I get the same distribution, but it's wider. You can see that the standard deviation is now 5. So one thing I want to warn you against, I'll show you in a minute. So people will often use the rand function to generate noise. So if we do the same thing, except we use the rand function instead of rand n, then what's going to happen is, so by scaling by 5, actually let me not do that for the rand function. I wish it would preserve my aspect ratio. So with the rand function, the histogram is totally flat. So your numbers between 0 and 1 are all equally likely. Some people might call this a step function because it actually drops to 0, below 0, or above 1. And that is actually not a distribution that is likely to happen in real experimental data. So I would suggest not using it to generate noise. It can result in some problems with regression. This is much more reasonable in most cases. One of the features, by the way, is that small errors are much more likely than large errors. And that is generally how things work in, quote, the real world. And also the shape of this distribution it is necessary for the least squares criterion, the sum squared error minimization criterion, to actually be the right one to use to get you a maximum likelihood estimation of your fitting parameters. So I do recommend including that in your in your fake data. So now what I want to do is use the rand n function to actually generate the same things that we saw in figure 1. Let's take another look at figure 1. So remember, this was the data set without noise. I want to add noise to it using the Gaussian distribution. So I'm going to make a third figure, and I'm going to plot the same things. So in fact, why don't I do copy the same code? And I'm going to change the word fake. I'm going to call it synthetic. Maybe that's a little more diplomatic, even though I don't know how to spell. Okay. And what I want to do here is introduce noise. Okay, so I'm gonna say noise standard deviation. I'm gonna set it to 30, and I'm gonna say y data 1 equals, what did I call? I called it y series 1 plus rand 1, and then length. This determines the number of points, so as many points as in the x series. The y series is also the same length. And now y data 1, 2, and 3 are going to be the same as y series 1, 2, and 3, except there's the noise. Okay, and now I'm going to plot y data instead of y series. Okay, let's see how that looks. Okay, so figure 3. Oh, you know what? I didn't scale. It doesn't look like there's much noise there, and that's because I didn't actually consider the standard deviation of the noise. There, I should get a bigger scatter. Okay, so now this might be what a real data set looks like. So here, the data are supposed to be linearly related, but you have scatter. Here, they're supposed to be quadratically related, so this should look like a parabola with scatter, and this is an exponential rise. Maybe a little hard to tell between the the second two, and I think we've accomplished our mission, but let's just put the three figures side by side. So this is our goal, right? We wanted what looks like real data. So that's essentially the straight line or the perfect curve with Gaussian distributed noise added. In the next videos, we'll fit these data to best fit curves and see if they resemble the parameters we use to generate the data.